Okay, so today we're going to start a brand new chapter. Chapter 10 is titled States of Matter. Stepping back from math, hardly actually no math in this chapter at all. So we're just going to talk a little bit about the kinetic molecular theory and what that is today, and then tomorrow we'll discuss liquids, and then on Friday we'll discuss solids, and then finish the chapter sometime next week and test out of this. So, kinetic molecular theory of matter objectives: state what it is, describe how it explains certain properties of matter, mostly gases, list 5 assumptions, and then compare ideal gases to real gases. Finally, take a look at characteristic properties of gases. So we'll talk about what expansion is, density, fluidity, compressibility, diffusion, as well as effusion. And then what does it take? What conditions are required for gases to be ideal, and then deviate from that and be considered real? So the kinetic theory of matter is basically this idea that particles of matter are always in motion. And so it does explain properties for ideal gases. A hypothetical gas that perfectly fits all 5 assumptions of the kinetic theory of matter. Or kinetic matter, yeah, kinetic theory of matter. Why do I have abbreviated KMT? But kinetic molecular theory, I don't know, whatever. Moving on. But the 5 assumptions. Assumption number 1. Gases consist of large numbers of tiny particles. They are very far apart relative to their size. Okay. Second assumption. Collisions do occur. And when they do occur, they are elastic collisions, which means there's no net loss of total kinetic energy. That means the kinetic energy remains the same as long as temperature is constant or the same. Okay, so temperature is tied to motion of particles. Remember that actually the definition of temperature is just the average kinetic energy an object possesses. Third assumption, gas particles are in continuous rapid random motion. They therefore do possess kinetic energy, and that the kinetic energy does overcome any attractive forces that these gases may have, except when the temperature of a gas condenses. Let's just say, this doesn't make any sense, but like if hydrogen gas condenses at X temperature, if that temperature falls to that X temperature, then attractive forces will be present. Okay. The fourth assumption, there are no forces of attraction between gas particles. They collide, but they don't stick. So over here, with our ideal gas conditions, particle sizes are small. The interactions between one particle to the next is insignificant, whereas with non-ideal gas conditions, we have some intermolecular as well as maybe intramolecular forces going on, or interactions between molecules. Finally, the fifth assumption is that temperature of a gas depends on the average kinetic energy that the gas has. And so it's abbreviated by this equation where the kinetic energy equals mass, 1/2 the mass times velocity squared. Now, like I said, there's no math, but I only stick the equation on here to show you that, like if you change the mass, if the mass increases, well then this number will also, your kinetic energy is going to increase. So all gases at the same temperature have the same average kinetic energy. At the same temp, lighter gas particles have higher average speeds versus heavier ones, and that just makes sense because they're lighter and yeah, they're just going to move faster than heavier ones. Now I just wanted to check something here. Okay.
Gas molecules and the physical properties of gases. The kinetic molecular theory views gases as being made up of large numbers of fast-moving particles that are far apart from each other. Most of the volume occupied by a gas is empty space. Gas particles are in continuous rapid random motion, and the forces of attraction or repulsion between them are essentially non-existent. Kinetic molecular theory relates the kinetic energy of gas particles to the temperature of the gas.
All right, so kinetic molecular theory, or kinetic theory of whatever, the theory does explain physical properties of gases and some properties of gases. Expansion. So when you put gas in a container, it's going to completely fill the container or take its shape. And this is based on assumptions 3 and 5. Fluidity. Gas particles glide easily past one another or flow. This is based on the fourth assumption. Low density, first assumption. Compressibility, also first assumption. Diffusion, okay, the process by which particles of gases spread out spontaneously and mix with other gases. And then effusion, process by which gas particles pass through a tiny opening into a vacuum, and that is directly proportional to velocities of the particles, how fast they are moving. Low mass effuse faster than high mass, because low mass means they can move faster. So here, gas at low temperature with low average kinetic energy, small little arrows. Gas at high temperatures, you increase that temperature, they move faster. If you remove the barrier, you have diffusion going on here. Okay, so properties of gases. Gases take the shape of their containers. Gases have low densities. Gases are highly compressible. They mix readily and diffuse, and they can also effuse. So,
gases differ from solids and liquids in that they expand to fill the shape of their container. Because there are large distances between gas molecules, gases have extremely low densities. Carbon dioxide, for example, is less dense than water, so bubbles of carbon dioxide rise to the surface. Gases are compressible to small fractions of their initial volumes. Because of this, large amounts of oxygen can be stored in tanks for scuba diving. Gases mix readily by diffusion. We don't have to stir or shake them to make them mix. Gases can escape containers through tiny holes in a process called effusion. This occurs when a bicycle tire is punctured.
all right, so just another diagram showing diffusion, where it mixes readily on its own, and effusion means it escapes kind of into a vacuum. Okay, now real gases don't behave according to the kinetic molecular theory. So noble gases and nonpolar gases tend to be ideal, but really there's no such thing as ideal gases, okay? But noble gases and nonpolar are the closest that get to it. But the reason for that is they just have less attractive forces. Noble gases have a full outer energy shell. They are inert. Nonpolar gases, there's no dipole going on. So again, less attractive forces. So the more polar a gas molecule is, the more attractive forces that go along with it that deviate from ideal gases. So I thought this table was really great that I found on the internet, comparing ideal and real, how we have some similarities, made of small particles that have mass, mostly empty space, low density, constant random straight line motion. But then here, no attractive repulsive forces, very small attractive repulsive forces. Particles have no volume, particles have a very small volume. Collisions are elastic. Over here, they are inelastic, which means that they collide and will lose energy. So that sums up 10.1, the kinetic molecular theory of matter. We just kind of went through all of these learning objectives. You do have an assignment. It's the 10.1, 10.2 worksheet, so work on the 10.1, and the next lecture we'll discuss the 10.2, which is liquids.